Et salut tout le monde. Bienvenue à Montréal-Python 99.1. Ben, vous devez- ben, d'habitude, on a les numéros de nos événements comme 97, 98 ou peu importe. Là, vous devrez peut-être vous poser une question. Pourquoi c'est 99.1? Ben, c'est parce que on est en train d'organiser notre centième événement. Ouais, c'est ça. On est rendu déjà au notre centième. Puis je suis tellement excité que je sais même plus quoi dire. Mais bon, en tout cas, on va essayer de faire ça toujours amusant et le fun comme toujours. En fait, on est en train d'organiser notre centième, puis on ne sait pas quand. Fait que on essaye de pousser ça vers l'été parce que ça va être plus le fun. Fait que on va faire ça en juin. Et c'est pour ça qu'on n'a pas de numéro qui, comme là, c'est 99, puis là, on va passer à 100, fait qu'on fait 99.1. Mais bon, ça va être ça. Euh, et c'est ça. Good. Hi, everybody. Welcome to Montreal-Python 99.1. So if you think that why is 99.1, it is because that we are organizing our 100 event, and between then we don't have a date for that event yet, but we try to do it in summer, so we're gonna have more fun, and because it's summer, so that's why we don't have another number for between 99 and 100, so that's why we use 99.1. So let keep in touch for that event. It's gonna be pretty cool. I have some ben, c'est ça, moi aujourd'hui j'ai juste une annonce, mais le centième, puis aussi le prochain Montréal Python, ça va être en personne. Ça va être le 24 avril en personne, puis ça va être chez Flair System, qui est notre partenaire. Et ben c'est ça va être toujours le même heure, 6 heures. Fait que, comme d'habitude, on cherche les présentateurs. Fait que vous pouvez déjà commencer à envoyer le. Je sais pas si vous m'entendez bien parce que j'ai comme mon ordinateur, il m'a comme popé des trucs bizarres. OK, c'est bon. Fait que I have an announcement for the next event. It is going to be in person at the Flare System, and it is going to be on 24th April. So we are looking for speakers who want to join us. We will try to do it in hybrid mode. So if you are not in Montreal, you can also submit your proposal. Okay. So that's it. Okay, and I just want to thank our partner, which is FGNA, who is hosting our after hour, which is going to be on Jitsi. J'aimerais remercier notre partenaire FGNR qui va hoster notre after hour sur Jitsi. Et oui, une dernière chose, c'est que toujours à Montréal-Python, on a notre code de conduite on veut que tout le monde s'amuse à Montréal-Python, et on veut que tout le monde soit gentil avec tout le monde, fait que si vous voyez quelque chose qui n'est pas correct, vous pouvez nous envoyer le message sur notre Slack ou directement sur le YouTube channel on va mais il y a Yannick qui est là online, mais je sais pas s'il y a d'autres membres de notre communauté qui est là, qui va gérer ça. Et last thing, we have a code of conduct at Montreal Python. So it is pretty pretty simple. So we want everybody to have fun and be nice with each other. So if you see something which is not nice, you can send the message to our Slack channel or directly on our YouTube channel. So that's it. Let's kick this one off. So our first presenter, I don't know how to pronounce his name. So let's bring him up and try to figure out how he end up with this cool name. So I let you present yourself to our audience, and I will be back then. All right.
Yeah, that's
Cool.
fine. Just let me know if you hear me well and you
Oh
see me
yes,
well.
yes, we hear
Okay.
you well.
Okay.
And then I don't know where is your. I don't see your slide. It's okay, Yannick. Oh yeah, okay, cool, cool. It's okay then. Yeah, I let you take the control of the. I'll be back. Okay.
Okay. So my name is actually Peter, so you can call me Peter. It's just the Polish version of the name. Should I start already? I guess so.
Yes. You can start.
Okay, okay. Because you went out, and I was like, okay,
Okay.
cool. Okay, so let's start. Let's start. Um, just bring the presentation because I'm not sure if everybody see it right now. Cool.
Yeah.
Okay. Okay. So let me just reorganize the windows on my side so that I would see everything well, and we can start. Cool. Okay. So, like I said, my name is Peter. I am a computer vision engineer based in Poland. But I work right now for US based company named RoboFlow, mostly known for the annotation tool, but we do a lot of other cool stuff. And my role is actually currently 50% computer vision engineer and 50% a marketing person. So I do lots of cool stuff. Most likely the coolest job I had so far. So let that be an introduction. But today I am showing you a project, a presentation that is not strictly related to what I do at work. It is a project that I done basically in my private time, and it is something that interests me a lot, which is basically how can we use computer vision in sports. And I done several projects like that in the past, and right now the latest one that I am interested in is using pose estimation algorithms to evaluate position of players. And this time in particular, I am talking about 3D pose estimation. And yeah, let's start. So the project that I done, this is the first stage of that project, is 3D pose estimation of a football player or soccer player, depending on where you live. Um, and the player is juggling the ball. So not only we are estimating the pose of the player, but we also try to understand the relation between the ball and the player and try to evaluate that. So this is the project that we will be covering. Okay, how can I do something similar at home or almost at home, but with limited resources. I don't have tens of cameras to use, so I was thinking about the minimum example that I can do to basically recreate at least partially the setup that they had during the Qatar World Tournament. So that's what I did. And the minimum setup that I used is basically a two cameras looking at the same player. So I simplified the scene. I only put one player and one ball, and I used two cameras. And those cameras were looking at the player. The lines between the camera and the player form 90-degree angle, and that's pretty important because that simplified my calculation by a lot. And Doc, is that to me? Because I am sharing my screen, so I hope it's not to me because I'm presenting the presentation for a few minutes now, so I'm a bit confused.
Peter, let me explain what's going on. So there's a private chat for people watching at home, and and we're staging the next talk. So Peter, you're good. We're seeing your slides.
Okay,
and we have the next slides in the pipe. So you're good.
Okay, cool. Thanks a lot for clarification, Yannick. Thanks a lot. Okay, so like I said, I simplified the setup. I used only two cameras. They're looking at the same person. The lines between the cameras, the person, 90-degree angle. That's it. So this is the data collection stage. The next part of the project was to align the videos. So I was recording. So that was not happening in the real time. I just recorded stuff, take it to home, and build the project. So when I was at home, I needed to synchronize those videos so that at both of the videos we are looking at exactly the same moment in time, just from a different perspective. That's what I did. This is the result of the time alignment of the video. Now the cool part, data extraction. So what I did is I used two computer vision models. The first one it was YOLA V7 pose estimation model. This is the model that can produce this 2D representation of person visible on a screen. And the second one was also YOLA V7 object detection model. So generally speaking, computer vision, those who knows, who has some experience, you know that we have like several quite frequent computer vision tasks like classification, object detection, image segmentation, semantic segmentation, pose estimation, etc. And those tasks are usually executed by completely different models. But quite recently, computer vision frameworks like YOLA V7 and YOLA V8 decided to add more and more capabilities because traditionally YOLA was a object detection framework. But with the recent releases, those libraries start to tackle more of those computer vision problems. And YOLA V7 is one of those frameworks that tackles both object detection and pose estimation. However, you need to keep in mind that you still need to run two different models to execute both of those tasks. So it's not like I have only one model and it magically do all of those things. I actually have two separate models loaded into the memory, and I run the frame through the first one and the second one, and then I annotate those frames with the detections. So that is what I did. YOLA V7 is quite cool because it's a relatively fast pose estimation model. It's not the most accurate one, but because I went for a very simple, scene, I only have one player with ball. I don't need high accuracy to be able to process that video, but at the same time I gain a lot because it's significantly faster, like multiple times faster than the regular models. Yeah, typically used for pose estimation. So I managed to extract the data, and now we need to put that data together to create our 3D animation. So before I can do that, I need to calibrate the data. So maybe let's start with a little bit of information about the pose estimation output. So when I run pose estimation model on the frame, I get, in case of YOLO V7, 17 anchors that are representing different points on the skeleton, on the pose. The cool thing about it, however, is that every anchor has information about what it represents. So it's not like I get 17 points and I need to figure out which is which one. I know that this particular point represents, for example, right ankle of the person. The other one is left ankle, etc., etc. So even though that I have 2 frames and I have 17 points on each frame, it is actually pretty easy to match the representation of the same anchor on both frames, because I only have one person. So I don't need to have like some math that would allow me to figure out which player is which. And I have all the information from the metadata perspective. So I can use that metadata to, match those anchors between the viewpoints. So that's the easy part. I can technically do it. Now the problem is that because I didn't put too much effort in the first iteration when it comes to aligning the scene, measuring stuff, and figure out what is where, basically, we have a small problem, small complication. So you can notice that the bounding boxes on the left frame and on the right frame have different sizes. And that's because the camera obviously has, those were 2 different cameras. So those cameras have different focal lengths. There is a different distance between the player and the camera. So it is a slight complication because we need to calibrate that information. So if I want to match the information from the left frame and the right frame, I first need to make sure that they, live in the same dimension space, let's call it this way, so that, the height, for example, of the player on the left and right side would be similar. So that's what I did. I used a simple Python algorithm to scale up, or maybe, scale, not necessarily up, scale both of those player to the same height. But at the same time, I kept in mind to keep the ratio between the width and the height of the bounding box, so that, I don't know, the player on the right side, who was smaller when I scaled it vertically, wouldn't get like super thin in one of the directions. And that simple process allowed me to more or less get a correct representation. Also, at the same time, we can for a second go back to the reason why we went with this very specific location of the cameras. So like I said at the very beginning, we located the cameras so that they form a 90-degree angle. So there is a 90-degree angle between the line connecting the first camera and the player, and the second camera and the player. And that's because it significantly simplifies the post-processing procedure. If I do it this way, I can basically assume that the first camera gives me information about the X, Z coordinates, and the second camera give me information about the Y and Z coordinates. And with that assumption, I can easily construct a X, Y, Z coordinates and just, what I did is I averaged the position on the Z axis, and I basically straight away took X and Y coordinates. We need to do those assumptions because we only have 2 cameras, so we don't have any extra information that we can use to make more educated guesses. We are basically bound to use that simplification. But as it turned out, that simplification wasn't as problematic, and the result is actually pretty accurate. So what we've managed to create is this 3D representation of the scene where we have a player and the ball. I spent, unreasonable amount of time building that matplotlib, by the way, representation of the scene, adding a little bit of an extra with the path of movement in 3D space for the ball and the feet, so that we can get a feeling of the movement and the kind of like the information where the ball was like a second ago or something like this. And this is the side by side. So here we see a video showing the player and a kind of like the skeleton representing the player in the 3D space. So this is basically the result of the project. Now I want to talk a little bit about the next steps and kind of like the problems that we faced in the project and how can we maybe solve those problems. So the first thing is, like I said, like I guess like 2 times already, this is very simple scene. We only have 1 player and 1 ball on the scene. And that's fine. But the moment that we introduce more players to the scene, we start to face a lot of other problems. So the first problem is that the moment I introduced a second player, we can imagine, like for example, on this this image right here, that we can experience occlusions, basically. So let's imagine that we would have a camera in the bottom right corner of that image, and we would basically, point it diagonally. That means that Steph Curry on that image would basically occlude LeBron James. And if we would like to use that particular approach to extract information about the position of, arms of LeBron, we wouldn't be able to do it with that configuration. Because we only have 2 cameras. 1 camera would be looking diagonally from bottom right to top left, and LeBron would be completely occluded. We wouldn't be able to get that information. So as a result, we wouldn't be able to, build a correct 3D model about, of his pose. So if we would like to tackle scenes where we have more than 1 player, we need to expect occlusion, and we need to take care of that. And, that's the first complication. The second complication is that when we have multiple cameras and we have multiple people, skeletons, objects to keep track, we need to be able to tell that skeleton A on the first camera is the skeleton A on the B camera. We have multiple skeletons. We need to come up with a procedure to match them together. And that's also not a trivial task to execute. So for that reason, it's another complication that we would need to face. But that's the second part of the project, and we are actually currently trying to tackle those problems. At the same time, we also faced some problems even with the 1-player scene scenario. So here we see false detections. Interestingly, on the left side, I understand why we get a false detection. So Chris, who was actually the player that we filmed, he's very fast. Even when we were recording at 60 frames a second, he's so fast that he can bounce the ball up, and in the time when the ball is going up and down, he can make a circle with his feet around the ball 3 times. So he's like extremely fast, and for that reason, on some scenes, depending on the lighting conditions, we got blurred frames. And when we got the blurred frame, the model was actually having a problem with evaluating where some joints are, because it was not completely obvious, and for that reason it was just guessing, and some of those guesses were incorrect. On the right frame, however, we actually have no idea why it made such a bad decision. This is actually pretty interesting, because on the single frame we got bad information on both cameras, and that may happen for multiple reasons: lighting condition, blur, but also at the same time just wrong detection from the model. And to mitigate that problem, we would actually go for models with higher accuracy. So slower models, but models that can give us better accuracy when they are processing the video. And this is something that we are experimenting right now to solve problems like this. Also, at the same time, in project like football, there is a problem with the set of anchors that we are using. So actually in post estimation, there are different sets of anchors depending on the data set that you use for training. And ELV7 is using 17 anchor sets. Like I said, I guess previously in the presentation. But that's not the only choice. There are actually sets that contain more anchors. Some of them even up to 33 anchors that form the skeleton. And that's another, thing that we need to take a look at, which is using more anchors and more accurate models to process. In the case of this project, what we experience is when you look at the presentation, the visualization, you can see that when he's bouncing the ball is actually not touching his feet, because there is no anchor on his feet. There is the last anchor is on his ankles. So it's actually a pretty weird effect, because when we show Chris juggling with the ball is actually like 15 or 10 centimeters from his from the last anchor that represent his feet. And this is something that we would need to we can mitigate by using different set of anchors, the one that can add additional information about his feet position. And the last thing that we can do to increase the quality of the prediction, and at the same time increase the quality of the model, is to use more cameras. So like I said, we use 2 cameras, and that is basically bare minimum if you want to execute 3D pose estimation with this approach, because you need to have information about 2 dimensions from one camera and at least 1 dimension from the other camera. And assuming that the cameras are not located at the straight line, that should give you enough mathematical information to model the 3D representation of the player. However, if we would like to solve the problem of occlusion that I described using the Steph Curry, LeBron James image, we actually don't have enough information, and we would need to use additional sources of information. And that means that we need to have 3 or maybe even 4 cameras on the scene to basically be able to feel the gaps in the model coming from some cameras where they experience occlusion. So this is something that we experiment right now. And the current state of that project is that we started to tackle those problems that I described. So we actually switched from football to basketball, and we constructed a scene where we actually have 3 cameras looking at the scene constantly, and we introduced another player on the scene to basically represent the situation close to the one that I was describing before. So we will experience occlusions, we will experience false detections over here, and we will try to solve that. This is something that I actually, the material that you see right now, I actually recorded this weekend. So I didn't really have a lot of time to play with it. I just throw a approach that we used to work, used to execute in the first stage of the project, because I really wanted to show you, to get the feeling of what types of problems we can experience with this sort of scene. And we already see a occlusion on the left and the right now. So it will be a ton of work to create a decent and reliable solution for that. But I guess it will be pretty interesting. And just I as always, I've thanked to Simon and the Chris, the guys who spent time with me recording those things and helping me out with data gathering. That project wouldn't happen without them. And that's it. If you want to take a look at the code, it's completely open sourced. You can find it at my GitHub. Here is the QR code that would allow you to easily find it. And yeah, that's pretty much it. That's the presentation.
Okay. Hey, thank you, Peter. Let me bring up Yannick, who will take care. Looks like we have a lot of questions there. So,
A lot of questions.
Yannick,
That's good. That's what I wanted to hear.
All right. Yeah, everyone, you can ask your questions on Slack if you're on our Slack, or in the YouTube comments, and I will relay them to Peter out loud. Je le répète en français. Tout le monde, vous pouvez poser vos questions sur Slack, et puis vous pouvez poser en français ou en anglais, ou sur YouTube, et puis je vais les relayer de haute voix à Peter. So Peter, first one is one of my questions. We've got a couple questions lined up after that. So if you look at motion capture pictures from video games or movies from a few years back, they all had those ping pong balls like stuck to their jumpsuits while they were doing the capture. You're not using any of that. You're not even dressing your model in something very recognizable. It was all a black outfit. So would that help, or are we completely past that technological stage?
So yeah, I guess you said from a few years back. I actually saw recordings of people making games this year, and they are still using that. So I guess that technology is still in use. I didn't really have a lot of information about the technology, but I shared that project on Reddit, and it blew up a bit, and people were starting to throw ideas, and that was one of those ideas. So you say maybe it could replace the motion capture procedure. So I actually digged a little bit. That suit cost $30,000 USD. So this is like, if you want to do motion capture right now, and you are like an indie developer, I mean, like you have a problem. You have a deep problem because that's pretty expensive sport if you want to do that. So that's one thing. You also need to have multiple cameras. We have like pretty good studio in Poland, the one that done Witcher, and I saw how they done motion capture for that. They have like 100 cameras looking at it. So not only you have that really expensive suit, but you also have like 100 cameras. And the short answer, yes. Obviously, it's not as precise. So it's kind of like the middle ground between having like a spot on representation, but paying like a ton of money, or having like a simplified representation, but doing that like almost for free. If you have 2 iPhones, you can do it. Yeah. So that's the answer. At the same time, the more cameras you add, the cleaner look you can get, and that should allow you to basically find all of those outliers, those back detection, and fill them with information coming from different camera, possibly more accurate. Yeah. In short, you should be able to use it. You should be able to replace that technology. But at the same time, NVIDIA is not sleeping. I saw stuff that they released like few or NVIDIA Unreal Engine, I guess. Unreal Engine is not sleeping. They are also releasing pretty cool stuff. So maybe we'll skip that part entirely and go straight to some super crazy deep learning algorithms. We'll see.
Excellent. On a similar note, Joe was asking, let me paste this question here, if drawing a grid or having points on the ground or in the background would help you to spatially locate where the action is going.
Yes, it would. Yes, it would. That's a short answer. I can elaborate. So generally speaking, the idea was to don't do anything like that, to kind of like have like completely natural environment, natural background. Like you also notice, like no suits, no additional sensors, stuff like that. But if we would introduce any of those, that would simplify my life tremendously, especially from the perspective of calibrating the image. So I was mentioning that was one of the key problems, and that problem grows the more cameras you have, the harder it is to calibrate that information. Having grid like that would be great. I actually experiment with something a bit different this time. So I'm not really sure if you are familiar with stuff called nerves. But that's actually kind of like the neural field that allows you to create kind of like the point cloud from the video. So this time when we weren't recording stuff, I actually collected information and I plan to build kind of like the 3D representation of the whole space just from a single video. That's possible. Maybe that's if you haven't have a presentation about that, maybe I can present, but it's pretty cool technology. And that also allowed you to just use video and nothing else to create like fairly accurate representation of the whole space that you are in. And I plan to use that for additional measurements and calibration. So I won't have the grid, but I will have a fairly accurate model of the whole space. And I plan to use it. So we'll see.
Cool.
We'll see. Fingers crossed that it will help.
Excellent. On still related to that, Pavel, I'm pretty sure I got that wrong. I'm very sorry. Is asking. So you answered some of those proposals. We're asking about deblurring the images, knowing shutter speed and the previous and the subsequent image. Would that be efficient and useful?
So it's Pavel, and I know because that seems like somebody who at least have Polish origins. So cześć if I'm right. And yeah, like any technical, hardware approach that would allow to mitigate the blur problem is obviously welcomed. So what you can do is have a better lighting conditions or have a better camera that would be able to capture the sharp images in high speed. And this is something that we also experimented this time. So we didn't have all of the cameras that would have this ability, but we have one that was capable of running 120 FPS with pretty sharp image. We are yet to evaluate if that helped, but in theory, having that would help. Deblurring the image, not necessarily, but having a hardware that can capture the crisp image is way better solution. With deblurring, you actually try to create something from nothing. You try to artificially create some information that was not originally on the scene, because if it's blurred and it's suddenly not blurred, that means that you use an algorithm that is artificially adding information that was not there in the first place. And that may, backfire when the other model that then used that information that was originally not trained on images that were semi-artificially enhanced, is not used to that and basically will behave weirdly. So it's much better to have a real image that was created with better hardware than to artificially fix the image. But in principle, that should help. Yeah.
Excellent, thank you. So that completes the questions. I'm just going to ask for one mini clarification. So you mentioned a lot about the hardware requirements for capturing the whole thing. What about running those models? Like, what kind of graphics card, computer cluster did you need to do what we
don't
saw?
need computer cluster, thank God. But I was running that on my GPU at home. I have RTX 3080, so fairly new card, but also not like godlike level of performance. And keep in mind that I was running two models at the same time, one for object detection, one for pose estimation. I was capable of running that in 15 to 20 FPS. And I could optimize that setup by using smaller models, for example, for object detection, because I was using model that was way too precise for object detection for that particular scene, because from the object detection perspective, that scene is super simple. One ball, one person. Pose estimation is the moment when it gets complicated. So I way overshoot when it comes to object detection. I could use smaller model, and that potentially could bring us in the semi real-time territory, assuming that I would get the result that I think I would. It would be 22 FPS, for example, 25 maybe. So that already sounds pretty interesting. Actually, when I was presenting the presentation on the meetup in Krakow, some person actually suggested maybe I could optimize it in the way so that I could bring my PC and those two cameras and actually run a live demo with somebody doing something, even holding the ball or throwing from one hand to another. But it is fairly possible to create a demo where that could happen in the real time. So yeah, that's one of the things that I have on my list. We'll see if that will happen, but that should be possible.
Very cool. We unfortunately have to move on, but we will post the link. Yes, we will post the link to your GitHub project in a way that is clickable for people who didn't get to capture the QR code. And thank you again.
Yeah.
And
I can send the links to the repo on the LinkedIn, so you can propagate it.
Perfect. We will do so. Thank you.
Thanks a
Thank-
lot for having me. Thanks a lot.
Thank you, Peter and Yannick. Let's move on to the next presenter. I will bring him up now. Hi, Salman. How are you?
I'm good, Ben. How are you doing?
I'm good. I don't see you. Did you share your screen yet? Or
Not yet. So
okay.
just
Yeah.
that.
Okay. Cool. So, Salman gonna talk about how to do the machine learning from scratch.
Yep.
I want you just to repeat it in French. I will let you go. C'est ça, Salman va nous parler de comment construire machine learning. Ça, c'est apprentissage machine à partir de zéro. C'est ça. Fait que, attendez, je vais juste acheter. OK, so are you ready, Salman?
Yep. I'm good.
Yep. Okay. So I let you take the control. Okay.
Okay. Sounds good.
Okay. See you.
Yeah. Thank you. So, hi everyone. Means I don't have one important thing. I don't have slides because I usually don't like PowerPoints. Means I'm not good at making PowerPoints. I usually am good with writing my stuff live and things like that. So that is what I would be doing. So I'm a private consultant, deep learning consultant, means I consult for different companies, means I have consulted for several different companies. Right now, I am a top talent from Omdana. And and my background, majority of my experience was academic. So that is the reason why this particular series. So I have recently started a series on my YouTube channel. So my YouTube channel is Data Scholar. And the series that I have started is simply machine learning from scratch using NumPy. So one thing that a lot of people, so on LinkedIn, a lot of people reached out to me because I post regularly on LinkedIn, and a lot of people keep on asking me the same question, that how to get better at data science and machine learning. The question is, majority of the tutorials that you see out there, they promote that you don't need to understand mathematics in order to be a data scientist or machine learning engineer or deep learning specialist. But the thing is, you can train the models, you can learn how to write the code. But the thing is, you can make the models, but you cannot tune them without knowing the mathematics behind them. So the previous presentation by Peter, it was amazing because he was talking in such details that it was showing that he had that knowledge in the background knowledge, which you need to know, not just how to model or how to train your deep learning models or things like that. So that is my whole focus here. And in this particular series, so I will not be going in detail. So here what I'm doing is I'm not skipping any mathematics whatsoever. So so you can see I have made 1 hour and 9 hour video, just the mathematical derivation of simple linear regression. And what I did over here is basically I derived from the scratch, did all the hard math and explained the intuition behind simple linear regression. And then we derived some formulas. So there are some formulas like this, the slope formula and the intercept formula. We derived it hard way. If anybody wants to go through the mathematics behind it, I would recommend you go check out those videos. And you can check out on Data Scholar YouTube channel. But what I would be doing in this particular presentation is implementing it using the code. So a lot of people, they learn Python, and getting better at Python it takes time. And if you want to get better at machine learning as well, then you need to learn Python as well. You need to learn machine learning concepts as well. So you can do both of them together. Why? Means if you just know how to be good at NumPy. So if you know NumPy is technically one library. You can model neural networks with it. So you can model all the models out there, for example, like linear regression or logistic regression or decision trees or random forest or support vector machines or deep learning models, all those deep learning ones. That you can model everything using just NumPy. So anybody who is getting started, I would recommend learn NumPy and then start coding every machine learning model from scratch. This way, what would happen is you will get better at NumPy and Python. And the second thing, you will understand the machine learning concepts, which are really handy when it comes to real world applications. When you go to data science, so when you go to data science interviews, when you attend data science interviews, they ask a lot of questions. For example, they ask some questions which you can only answer if you understand the background mathematics of those models. So for example, like I have given a lot of interviews, and in those interviews, people have technically gone in detail. For example, they pick up one machine learning model. They ask which model you are comfortable with. And then, for example, I say I'm good with linear regression. Then they're gonna ask me questions related to linear regression in so detail that they want to see whether I understand linear regression or I just know how to code, how to just write 3 lines of code in scikit-learn and get done with the model. They don't want that person who just know how to write 3 lines of code. They also are looking for something that you need to know how to hyperparameter tune your model, means which hyperparameters influence your model in what particular way. So right now I would be coding simple linear regression, multiple linear regression, and rich regression from scratch, and you would see they are pretty much very simple. If you want to go behind the mathematics of it, I would recommend you watch the videos on the channel. But if you don't want it, I'm giving you the formulas right in front. So this is the formula for the slope for simple linear regression, and this is the formula for intercept for simple linear regression. And that is what is used behind linear regression class of scikit-learn. And we would be implementing it and comparing it with scikit-learn. So sorry, my bad. So what I'm going to do is I will open up Google Colab and I will start noting down certain things. For example, I need to implement. So these are the formulas. I have written down these formulas. The easy thing about Python is, or these mathematical notation is, you can see that these notations are usually very scary for beginners. A lot of people get scared when they look at this summation sign, I equals something from something. So here I can put it from 0 to onwards. That would be good. So wherever you see this summation sign, that means you need to use a for loop, and this for loop needs to go for the I value in the range from 0 to n. That means it should go for I in range from 0 to n. And that n value could be anything. It would be number of data points that you have in your data set. So which means if I see this m value, technically, I need to run a for loop for the numerator, and I need to run a for loop for denominator. And similarly, the b value totally depends on the m value. Once I get the m value by running these 2 for loops, I can substitute it here and I can find the b value. These y bar terms over here that you see are the mean values. So this is the y mean, and this value that you see over here is the x mean. And similarly over here, this is same y mean and this is same x mean. That means if you want to implement simple linear regression in your own code, it's pretty straightforward. And let's get to it. But before I get to that point, we should have some reference. Means we know that we are creating our own class. At least we should be comparing it with something we know is true, is right. Because if we are creating a class and we are doing something wrong, we need to at least make sure that our results are comparable to something. So what I'm going to do is I'm going to start with simple scikit-learn's implementation on a regression dataset. So for regression dataset, I will create my own regression dataset. So let's start with that. So I'll start with maybe. So I'll start with So I will just simply import the make regression from scikit-learn, and then I will define the random state for repeatability purposes. So I will give it a number. You can give it any number. I usually go with 22. That's my favorite number. And then I will generate the data set. So how I would generate the data set, I will say I will get X value and Y value, and I will do the make regression. And in this make regression, I can introduce how many samples I need. So here you can see that I'm only creating 100 samples. So let's substitute number of samples equals 100. So here we got the number of samples equals 100. Then I need to tell it how many features I need. So number of features I need to tell it. Since we are doing simple linear regression has only one X variable and one Y variable, which means I need to have just one feature. I would also add some noise in my data as well, because I don't want all the points sticking on the line, best fit line. I want them here and there. So I would just introduce a factor of 10. Then I will put in my random state. So I just created my data set. And I also want to take a look at the first 5 values of my X and first 5 values of the Y. So I'm going to just print them out. So I'm going to say X. So my X values are simply, I will just print out the first 5. So I would say first 5. Then I will also print the Y values. So Y values would be, I would print out from the start till index number 5. Let's print it. Here you can see these are my first 5 X values, and here are my first 5 Y values. But right now I created a data set, but I don't know how it looks like, whether it is a real regression, can a straight line fit on it or not. So visualizing would be a good deal in this scenario. So let's quickly visualize the data set. For that, I will quickly import matplotlib. So matplotlib, let's import it. Now I will create a scatter plot. So I will put the X variable and Y variable. I also would like to set my axis labels and title as well. So let's do plt dot x label. And what I would be getting over here is, what should I do? Since it is a feature, I would just call it a feature. Then I would do Y label, and I would call it maybe target. So, and then I would put it a title as well. So plt title. So I would give it regression dataset. And let's show the plot. So plt dot show. So when I run it, you can see I just generated a random regression data. But keep one thing in mind. I have put the random state equals 22, which means no matter what, whenever I want to create this data set, I will create the exact same data set if I keep my random state equals 22. If you also keep that, you would be getting exactly the same data set. As you can see, this data set does have a trend. The X and Y do depend linearly, and I can put a best fit line, and that would be a good model in this particular scenario. So now I'm going to implement simple scikit-learn's linear regression class. So what I would be doing is I would be quickly importing scikit-learn's linear regression module over here. So I will import linear regression, And I would also import NumPy as well, because we would be using NumPy. So let's import both of these modules over here. Now, creating a machine learning model is pretty straightforward using scikit-learn. First, let's introduce our model. So model underscore, I would call it scikit-learn. Since this is my scikit-learn implementation, I would just do skl, and then I would just put linear regression. So I just introduced an object, linear regression object over here. So I just instantiated my model here. Now I would just simply implement it. So skl dot fit. So you just use the dot fit method of linear regression module and you would fit the data. It takes 2 arguments, as you can see over here. It takes x and y, and then there are some sample weights. Right now we don't care about those sample weights. So I would just put in x and y. So this should fit the model. When we fit the model, that means it's going to learn the intercept and slope of on our particular data set. Let's print the slope and that data set. So I will print the slope and I would print the intercept in this particular scenario. So let's print it quickly. So I would say intercept would be model underscore skl dot intercept underscore. So this is gonna give us the intercept, and then I'm gonna print the slope as well. So slope, and that would be model underscore scale dot slope. So this would be coef, I think, because in scikit-learn they use coefficient, so they don't call it slope. So I would just give it coef underscore. This is gonna print it. Now this will print it. Let's print it. Let's take a look. So see, you can see it printed the intercept and slope. So this is the intercept, which means where it is cutting the y-axis, and this is the slope on my data. Now let's generate some prediction data. So remember, I just created my regression data set, and in this regression data set, I did not split it, but that's a good practice because I did not split it, so I don't want to use any of the data points from this x. I will just use some random new x values. So I will just create some random new x values so that there is no data leakage in this particular scenario. So let's generate it using NumPy. So I would call it x new. So I would use NumPy array over here. And let's generate some data. So I would call it maybe 0.5. I will take one value over here. Then I would do maybe -1. And then I would do maybe, let's do 2.0. So this is the new values. And I want to predict what would be the y value for these new x values. So I would do y underscore pred underscore skl. So I would do model underscore skl dot predict. So I'm using dot predict method of the linear regression module, and this only takes in the one x variable. So here we want to find it on the new x values. So I will just put in new, and this is going to print it out. I did not print it, so let me print it. So print y underscore pred underscore scale. So here you can see that when what this prediction is telling me that when the x value is 0.5, the y value should be 18 point something. When the x value is -1, the y value should be -38. And when it is 2.0, it should be 76.279 something. When we create our own class, we want to get the same results. So this is why exactly I got these results, because I want to get the same results using our own class. So this is our now control. So we would be comparing everything with this. If we are getting the same results, that means our class is working absolutely fine. Now, obviously, this is just giving you an idea, but let's visualize the best fit line on our data set as well. So for that purpose, what I would be doing is I would be just creating the same scatter plot again and put a line on it. So for that purpose, what I would be doing is simply I would predict underscore skl. I would call it model dot underscore skl dot, and I would predict it for all the x values, not the x new value, all the x values. I want the prediction because I want the line on all the real data. Now let's quickly do the scatter plot. So over here we have plt dot scatter. So, and then it's going to take the x variable, and then it's going to take the y variable, because I want the scatter plot to be exactly the same we got previously. Now let's plot the predicted line. For predicted line, I would do simply plot, and then inside over here, I would give x and then y underscore spread underscore scale. So this is what I would be giving. And then I would give it a color as well. So let's give it a color, maybe red. And I can set the access label and title, but for now, I'm going to skip it. I will just move on to the show part. So plt.show, let's do it. So when it goes through, you can see scikit-learn is predicting it very amazingly. So we should be getting some similar results when we create our own class. So when we create our own class, let's create it. So remember, when we are creating our own class, we are keeping in mind these formulas. So these two formulas are the key over here. So since there is a lot of mess, so I will just move it around. And so first thing, I want to implement this m. So what are the things that I need over here? I need the mean value of y, and I need the mean value of x. So this mean value of x, mean value of x, mean value of y. So let's find the mean values of x and y first. So here I will be creating my own class. So first thing first, I would be starting with, so let's give it a name. So what name you would be giving it? Maybe I would just give it class, and I would call it simple linear regression. And I would just, this is my class name, simple linear regression. Now what I'm going to be doing, I would be creating a constructor to initialize instance variables. So for that purpose, I would be using the dunder method init. And then here it would be self, and then anything else? No, I don't think so. So I would just put it here. And then here I would define all the variables. So we have slope and we have intercept. So let's define it. It would be self dot intercept, and I would initially call it none, and then I would call it self dot slope, and I would call it none in the beginning. Then we should have two different methods. So one should be the fit method. So we should have a fit method, and fit method should take certain parameters as an input. So it should take the x variable and the y variable as an input. And after that, we should have a method which we are going to call the predict method. Remember, we use the two methods, one fit and one predict. So we would be doing exactly the same. So this predict method is also taking the x variable as an input. So I would just call it x variable and then give it a pass. Now let's start filling it up. So over here, what I'm going to do, first thing first, I would be, if you look, I have a loop. So this loop is running from I value equals, so it should be 0 to n. So I need to calculate this n value. So let's calculate this n value. So I would call it n, and I would say it is simply the number of data points we have in the x variable. So it would be the shape of x, and I would just take the number of rows. So I would just take number of rows. So this is my n variable. The second thing I can calculate is the x mean. I can calculate the mean pretty easily. So np dot mean, and I would do the mean of x. So this would give me the x mean. I would also do the y mean. So y mean would be simply, and I would do with y. So we just calculated all these things. Now you can see in this m variable, I figured out what this n variable is, and I figured out what are these mean value y mean and x mean is. And now I need to run the for loop for the numerator and for loop for the denominator. So since both of them have the same range, I value 0 to n, I value 0 to n, that means I can just create one single for loop. So let's create the for loop. So for loop will run for I value in range. So what range? The n value. So that would be the range in which it would be running. So this for loop. Now in this for loop, I can do is I can calculate the numerator separately and denominator separately. So what I'm going to do, I will define two variables over here. I will start my numerator to be equals to 0. And then I would say my denominator is also equals to 0. This for loop is doing what? It is doing summation, which means it will calculate this product and then it will add it into the next value. Then it will calculate the product of the next value, add it into the previous one, add it into the previous one, and that is what it's going to do. The same thing with this, it's going to calculate this square, add it into the next one, add it into the next one, and so on. So since I need to calculate numerator, initially it is 0, which means we will calculate it for the first value, then it will store it in the numerator, then it will calculate for the next value, and then add it into the previous value, and it will keep on doing that. And that is what I'm going to do over here. So over here, I would just say that numerator, and it would be plus equals, which means I will keep on adding into this num variable whatever the value we are going to calculate. So what are the value we are going to calculate? Yi minus y mean. So let's do that. So it is pretty simple. So it is y I. It is straightforward as it is, as you see on the equation. I'm substituting it over here. So it is minus y underscore mean. And then I'm multiplying it with what? I'm multiplying it with, you can see, xi minus x mean. So I would do exactly the same thing. Xi minus x mean. So I just did that. So this is my numerator. So I just figured out my numerator in this particular scenario. Now I can find the denominator exactly the same way. So my denominator looks something like this. It is xi minus x mean whole square. So I'm going to do that. So it is xi minus x mean, and I want to do whole square. So this would give me the numerator and denominator variable. So once I get that, my for loop is done. Now I need to calculate my slope. You can see now I can calculate m value, which is the slope, and the b value, which is the intercept, pretty easily because I can calculate the numerator and denominator. My slope would be pretty simple. My slope would be numerator divided by denominator. And my intercept would be simple. As you can see over here, the mean value of y minus m times the mean value of x. I'm going to do that. So y mean minus self dot slope times x. So let me double check. So this is what we get. And now I don't need this. So which means now we have our fit method completely defined over here. Now I don't need to introduce a return. I would just skip it. Predict is simply our equation. Y is equals to mx plus b. So which means whatever m you calculated, you substitute here. Whatever b you calculate, substitute here. And whatever the new x value you have, substitute here. It will give you whatever y value this model is going to predict for it. So I'm going to implement it straight away over here. So here I would just give it the return statement, and in the return statement I would call it slope. It should be multiplied by x, and plus I would add the intercept. So this is the m value multiplied by x, mx plus b. This is what we should be getting as a result. Let's define our class. So I just defined my class. Let's quickly implement our class and see if we are getting the same answer or not. So create a simple linear regression object. So I would call it model underscore our simple linear regression. So I would just call it simple linear regression, SLR, instead of SLK. Or I would just leave it as model. Just keep it simple. First thing I would do is simple linear regression. So I just define an object, simple linear. Now let's fit it. So model dot fit, and I would take X variable and I would take Y variable. So it should fit. Next thing, I want to print the slope and intercept. So let's print it. So I'm gonna do slope. First thing first. So slope would be pretty straightforward. I can do model dot slope. That's it. And then I would print intercept as well. So intercept would be pretty straightforward again. So it would be model dot intercept. So let's print this and see what kind of a result we are getting. So I'm getting some kind of a result over here. So model dot intercept. So did I do something wrong here? I did not put a comma here. So let's put a comma here. Now let's implement. Here you can see our slope is 38.38. Our intercept is -4.8. If we go back up here, the implementation of scikit-learn, we were getting exactly the same. You can see if you can match a lot of zeros over, means a lot of decimal places, we are getting our answer accurate to those decimal places. That means scikit-learn is implementing exactly the same formulas in the background. And how we get those formulas, if you want to get behind that, I would recommend you check out the videos where I'm breaking down everything from the scratch for people who don't even know calculus or something. So, so we just implemented our own class. And if I want to generate a new data, so we have already generated a new data. Let's do predictions on that. So see if our predictions are exactly same as the predictions we got. So since our slope and intercept are same, we should be getting the same predictions on the same X variable. So let's do that. So y underscore pred, I would call it. And I would say model dot predict. And I would take it X underscore new variable. So when I do that, so it's not going to give me because I did not print it. So let's do y underscore pred. So let's do that. So here you can see it's going to give me three values, 18, -38, and 76. If we go back up here, we get 18, -38, and 76. So we are getting exactly the same results. Okay. So this is simple linear regression, but keep one thing in mind. The formula that we implemented over here is a very simple formula. It does not use linear algebra whatsoever, which means this particular implementation would only work for simple linear regression. What is simple linear regression? Simple linear regression is when you have just one X variable and one Y variable. That's it. If you have more than one X variable like X1, X2, this implementation is going to fail. And that's where multiple linear regression comes into play. So multiple linear regression is pretty straightforward. So regression, multiple linear regression, the formula for multiple linear regression looks something like this. So in the multiple linear regression of scikit-learn, they do not use these formula as it is because these formulas are very basic. You need to have them in linear algebra or matrices form. So when you convert it into matrices form, then you can use it for multiple features, x1, x2, x3, and so on, and one y variable. So the formula for that is simply, you don't calculate m and b separately, you just calculate the betas, and that betas contain the m value and b value, all of them. So this betas is basically equals to x transpose times x inverse, and then outside it would be x transpose times y. This is the formula. If you want to get behind the maths of it, I have recorded a complete video on it, which I would be posting most probably by the end of today. You can check it out. You would be able to see how we get to this formula from these two formulas. Okay, so I would be quickly implementing multiple linear regression here, and I would show you that it works absolutely fine. So let me go back here and let's create our own class. So what I'm going to be doing is I will be creating my own class. So let me quickly open up a data set. So right now we don't care about the data set. Let me implement the class over here. So I would define my own class, and I would call it multiple linear regression class. So this is my multiple linear regression class, and I would define the init vendor method, and I would have a self, and then I would also do self dot coef. So I would just do coefficients. I would just keep the terminology same as scikit-learn here, and I would do none, and then I would do self dot intercept equals none. It is exactly the same as we did in simple linear regression. Now what I'm going to do, I will define a fit method. So the fit method is going to take the same inputs x comma y, and then what I would be doing is I would be first. So when we do this particular thing, first thing we have to do is there is one simple thing. When you convert it into the linear form in matrix form, so matrix form looks something like this: ax times beta. This is the equation. Or you can say y is equals to x times beta. So what is this x column over here? This x column is technically all the x1 and x2s, but the first column is full of ones, the values ones. Then it would be x11, then it would be x21, and so on. Then it would be x12, x22, and so on. And this it would be x1n, x2n, and so on. And then over here, these betas are technically the first value is the b value, and all the other values are m1, m2, m3, and so on until mn. Which means when you take the x variable, all the x variables as an input, this particular data set, that means I need to add a line or a column of ones before it. And that is what I'm going to do over here first. So in scikit-learn, they also use a copy method, copy x method, which means they are also doing in the background this particular stuff. So here, if I say that, if I add that column and I would label it as capital X, it's going to change my original X. I don't want to do that. So here, I'm going to give it a different label. So X new, I would call it. And this X new, so maybe not X new, maybe X power or x1. Let's do it. So this is x1, or maybe let's do train. I don't like to use numbers. X train. And what I would be doing, I would be doing np, and I would be inserting in this x variable, whatever our x variable is. I would put kind of like a column of ones. So since it would be at index 0, and I want to put at index 0 value 1, and then my axis should be the columns. So I don't know what is happening here. So my axis would be 1. So what this is going to do is it's going to add one column of ones before our x variable. So when you split out your data set into x and y, then the x column should have 1 at the start. So we are just adding that column over here. What is the reason behind it? Right now, I cannot address it because that's a complete background mathematics behind it. I just gave a good overview over here why this is needed, because we don't have mx plus b. All of those things are added here because it saves computation time. And that is the advantage of linear algebra and matrix form. That is the reason why linear algebra is very important to know. So over here, you can see that I just did that. Now the next steps are pretty much same. So I would call it betas, and I would do linear algebra. So np dot linear algebra module. That is what I'm going to use over here. So linear algebra, and I would be using inverse. As you can see, this equation, it has an inverse. So I would be doing inverse of the dot product of these two things. So these are matrices. These are not simple basic products. I cannot use a static here. I would be using dot product here. So I would be just doing over here. So np dot product. That is what I'm doing over here. So and I will be taking the dot product of x transpose. That is what I'm doing, and comma I will be doing it with x. So this is the dot product I'm talking about over here. Then this whole thing is getting multiplied by x transpose. So let's take a dot product of this whole thing, dot, and I would be doing x comma transpose, and then I would be doing, it should be in the brackets. So and then I would be doing the dot product with what? With the y variable here. So this is my y variable. So I would just call it a y variable, and that should be my betas. And if you see this particular equation, you can see the first value is the intercept and rest of the others are the coefficients, which means I can evaluate the intercept and coefficients pretty straightforward. So intercept would be simply betas, the first thing or the first item in betas. That is what my intercept is. Whereas dot coefficients are simply betas, everything from 1 onwards. So these are my betas. I just define my fit command. This is my multiple linear regression. This would work for any data point. Now let's quickly define the predict method, and I will show you implementation on another data set, maybe diabetes data set or something else. So let's do our define. Predict would take x as an input, and then I would have return, and I would return np dot product of x comma self dot coef. So this is technically mx I'm doing. So this is mx plus b. So I would do plus, and what is b? It is the intercept dot intercept. This is our class. Now let's quickly implement it on simple basic data set. So which data set I would be using here? I would be using diabetes data set from scikit-learn. So I would quickly import it. sklearn dot datasets import load diabetes. So let's load it and let's define it. X comma y equals load diabetes, and I would say return underscore x underscore y is equals to true. So I would do that. So my bad. So this should be capital T. So let's do that. So here you can see this is x and this is y. Here I can print x. So you can see this is what x looks like, and here I can print y. Here what y looks like, and I can print the shape of it. So you can see, there should not be any bracket. So this is the shape. You can see it has 442 and 10 columns. So 442 data points, and there are 10 variables in total in the x, and in the y, I can check the shape of the y as well. So shape of y is 442 and just one column. So what I'm going to do here is I'm going to implement our class. Yes, I have to do train test split, but right now I'm going to skip it because I would respect the time over here. So I just want to finish it and get done with this presentation because I think this has been extended quite a while. So what I'm going to do is I would quickly, so I'm not using train test split. I'm just implementing our own class. So first thing first, I will define our model underscore multiple linear regression. And that is simply multiple linear regression class. So first I define that. Then I will fit this one model underscore multiple linear regression dot fit, and I will fit it on our x data set and y data set. So this is what I'm doing over here. And then I want to print the intercept. So intercept would be pretty simple, model underscore MLR dot intercept, and then I'm gonna be printing coeffi LR dot, I don't know what I did here. Slopes. When I print the slopes over here, it would look something like this: model dot MLR dot coef, and let's do that. So simple linear regression object has no so did I do something wrong? Model underscore MLR model. So this should be underscore. So here you can see that this is the intercept and this is the slope. Now, whether we are getting this right answer or not, let's quickly implement scikit-learn's implementation. So scikit-learn, we have previously defined our model underscore. So I can quickly define sklearn's model, and that is simply linear regression model. So and then I will fit it model underscore sk dot fit, and I will take x comma y, and then I will print the slopes and everything just like that. So I will copy this, I will paste it. So if I paste it, it would be model underscore sk, and this would be sk, and this should have intercept underscore, and this should have coef underscore. If I print it, if I train it, you can see our model is not doing the same thing. I did something wrong here. So am I taking the x value here? Okay, so seems like I have made some mistake somewhere here. I think I need to double check it. But this is the implementation. I think most probably I just need to play with some numbers here, and we should be getting it. So let me double check. So I'm doing np dot linear algebra dot inverse, and then I would be doing dot product of.
Salman, I think I spotted it. I think you're not using the X train that you built with the column of ones.
Oh, yes, you're right. So this should be. You're right. So this should be X train. This should be train. This should be train. Thank you. And I think so. We should be good now. So let's implement it. Let's run it. Let's run it. So 152, 152. So now we are getting exactly the same result. So 152, that is intercept. These are the slopes, -10, -239. So -10, -239, and so on. So you can keep on playing with that. Means I can just change few bits over here and I can convert it into ridge regression. And I can change few bits over here. I can convert it into lasso regression. For example, if I have to change this into ridge regression, the only formula I'm going to change this beta. So if I want to do ridge regression has the same formula. The only thing I have added in this particular formula is, so this is x transpose, just like that. Then it is multiplied with x, and then I have plus alpha times identity matrix, and then I have an inverse, and outside it is pretty much same. You can see it is exactly same. The only term, this term, is added up. And this alpha is one of the parameter which tells you how much regularization you need to do. If this is 0.1, then it's going to do some regularization. If it is 1, 10, or 100 or whatever, you can play with this factor and it's going to introduce L2 regularization. And similarly, when we do lasso, it's a bit different, but it is very similar. So the whole idea of this particular presentation was, or this particular going through is, if you are learning machine learning, I would recommend you, or if you're getting started with programming, I would recommend you take things side by side, learn one algorithm at a time, and try to learn code from scratch. This way you will learn the coding. This way you will learn the machine learning algorithm. You will learn the background mathematics, which means during the interviews, you will ace your interviews. That is my promise to you. You will do that, because I have been doing that, and All those interviews, the technical part, whenever interviews talk about these background mathematics, I usually ace those parts. So I think that is the end of this session. If anybody has any questions, please feel free to ask me. Thank you so much.
Thank you, Salman. I don't have question, but I mean, we love live coding, So thank you very much. I will not gonna bring. I will bring up Yannick, and he will take care of the questions. Yeah. Thank you, Yannick and Salman.
Yep. Thank you so much.
Thank you, Salman. That was very impressive. Your nerves of steel to type all this code while live. That was very instructive and entertaining. So everyone, same thing as for the previous presentation. You can type your questions on Slack or on YouTube, and it will be my pleasure to relay those out loud to Salman. So Salman, while everyone is thinking of their questions and typing them furiously, I have a question of my own.
Yes, sure.
What input device are you using? Because you were able to write beautifully on the screen, so it seems to be a stylus, and there's definitely way beyond what I could do with a mouse or touch stick like I'm using.
So, I'm using this Wacom. So this is the tablet, Wacom tablet. So I'm just using that. Yeah.
Very good. You're mastering it. That's very beautiful. Let me see real quick if we had some questions. I don't see any. Maybe because it was very clear. I'm going to have another question of my own if we don't get questions from the audience. I don't see any questions from the audience. So one benefit of scikit-learn is that everything is implemented, but you made a very solid point that implementing it yourself will allow you to better understand what's going on behind the hood and then tune the parameters. What would be the other benefits of scikit-learn? Is it going to be more performance? What kind of how far can you take your hand-coded models with NumPy? And when do you start to have to think about, okay, I'm going to move that to CUDA, or I'm going to use scikit-learn? Who's going to use CUDA behind the hood?
So the answer to that is this is for learning purpose, because scikit-learn in the background is already using NumPy. So scikit is using that. So which means all the models that are running in the background, they are using these basic NumPy scientific computing modules. But the whole point of creating your own classes and everything is a learning purpose, or getting the feel of how in the background scikit-learn is making. So yes, in scikit-learn, you can just do .fit, .predict, and you are getting the results, but you don't know which parameter means what. For example, like if you go in Ridge, there are 7 different types of solver in Ridge in the background. And one of the kind of like the equation that I showed you, that was only for one solver. There are 7 different types, which means they have in the background 7 different formulas which are running for just one simple Ridge model. That means if you know which particular solver to use in which particular scenario, and which one is going to work well, if you understand the mathematics behind it, that would be pretty easy for you, because that part is part of the hyperparameter tuning. So if you understand that, then hyperparameter tuning would become easy for you, because you know which parameters to tweak. It's kind of like a guitarist, when he's tuning his guitar or something, he knows which notes are playing well. I mean, he can just listen, means not even looking at the device, he can listen. The same way, if you are a machine learning expert, you can just see, oh, maybe just I need to change that particular solver, maybe just I need to change the value of alpha to this, or things like that. And it gives them results. So understanding that is something the focus of this particular thing is. And one more thing, JAX is another library, which is kind of like we can use kind of like, which is very similar to NumPy. Mm-hmm. And its syntax is very, very similar. And you can implement all your code in JAX, and you can run all your machine learning algorithms, which scikit-learn has, on GPUs. So which means you can run simple linear regression on GPUs. You can run random forest on GPUs. So yes, we have XGB, which you can run on GPUs, but there are so many others like random forest. We have KNNs or something. You can run those on GPUs, because if you learn NumPy is kind of like I have seen that if you learn NumPy, you can ace machine learning anywhere. I mean, JAX is something people are kind of like, for example, we have TensorFlow, we have PyTorch, but JAX is coming up, and it is very, very, very dynamic programming. Means it's kind of like means I really don't know the technical names, but it's very easy to implement, and you can just use JIT in it, just in time implementation, and it can kind of like fast or processes fast your machine learning model, or you can train your simple basic models on GPUs. So that is the advantage you can get. So learning it is one point, and then you can take it to JAX, and you can just convert it into GPUs. Yeah.
Very good. Fantastic. That's a perfect conclusion for that that path that you took us through. We unfortunately have to move on. Salman, I would like to ask you many more questions, but thank you again for sharing with us.
All right. Thank you, Yannick and Salman. Thank you. Let me bring up our next presenter, who is Alexander. So,
Oh, sorry.
hey, Alexander. How are you?
Good, good. I didn't anticipate it getting dark before I went, so sorry, you're gonna have trouble seeing me.
Yeah. Did you share your screen? Then? I don't see you any share.
Here you go.
Okay.
So I'm gonna share the entire screen.
Mm-hmm.
All right. Can you see it?
Yes. I added it here. Okay, cool. So,
excellent.
Okay, so are you ready?
Yep. I'm
Okay,
good to
I
go.
let you take the control of the whole thing. Okay, I see you later.
All right. Excellent.
Okay.
Hi everyone. So today I was thinking about introducing one of my personal favorite Python libraries. Typically in my experience, a lot of data scientists have a lot of trouble translating and deploying their machine learning models to a usable state for the user. And typically, like, a good way to do that is with dashboarding. Now, with a lot of dashboarding, I always feel like they're either too close to the system, like Flask or Dash, where you have to use like HTML and CSS, and you have to manually do all of your callbacks, or it's a little bit too far away, like Tableau or Click, where implementing the machine learning within your dashboard tends to be very difficult. So the library I want to introduce you all today is called Streamlit. Now, the beauty of Streamlit is that it's a very Pythonic library that takes a lot of script that creates dashboarding purely through scripting. So you don't have to use any HTML or CSS or extremely strange syntax. It's just very basic Python code that will essentially create your library, and everything that involves more of the back end of whatever dashboard that you're creating is kind of done in the back end of it. So I would say that what's really cool about Streamlit is that it's extremely intuitive for a lot of Python. It's an application library that's very intuitive for a lot of Python programmers, and it's very easy just to pick up and learn and start translating exactly what you need to what you would like to deliver to the user into code extremely rapidly. Now, I kind of want to go into how Streamlit works. So Streamlit interacts with the user through the use of widgets. Now, widgets are essentially the flavor of different inputs that your user is going to bring into your library, into your dashboard. So you can kind of consider like a radio button a widget, a switch a widget, a checkbox a widget, so on and so forth. And what's really cool about Streamlit is every single time a widget is used or the source code is changed, the dashboard will update automatically and will rerun the script, your current script, from the start. So what you end up having here is a very powerful interactive dashboard that takes in various user inputs and processes them via just basic Python code. So really cool. And then what I really like about Streamlit, as opposed to a lot of other dashboarding libraries, is that it has such a wide variety of different tools and different output tools like Plotly, Matplotlib, Seaborn Plot, as well as different type of text formatting tools like LaTeX, Markdown language, and these can be used to format the text within your dashboard when you're creating it. So not only can the customizability in the back end be really easy, but even the front end and the formatting can also be very intuitive, and especially the formatting of the dashboard. I'll go into how you can format Streamlit a little bit later. Now, the advantages of Streamlit is that it's very easy and intuitive for Python programmers to use. It's compatible with even though you don't need HTML to use it, it's still compatible with HTML, CSS, and JavaScript. It also has built-in functionality where you can implement your Markdown text or LaTeX if you want to write some type of mathematical equation into your dashboard. It's also great for image handling displays. And then on top of that, it's very easy to format with different columns, different tabs, and it allows for very seamless integration of your machine learning model. So without further ado, I can introduce you to I'll go through the first part of my project, and then I'll introduce you to more of the Streamlit stuff as well. So I thought it'd be very pertinent to kind of show you where the ML in this dashboard is going to come from. So for this particular project, I decided just to use a simple housing data set I found on Kaggle. It takes various attributes, and then it translates that into the price. And you essentially use multilinear regression or any other type of regression. For me particularly, I decided to use random forest regression in order to predict the price. So going through, you can kind of see of the
Alexander, pardon my interruption. Do you think you could increase the font size just a little bit for the people who do not enjoy such a great resolution? That's perfect. Thank you so much.
Excellent. Okay, good. I'm very happy you can see that because I'm just zooming in. Yeah, sorry about that. Yep. Yeah, thank you for the interruption. I want people to see. So I start first by reading in the data, getting an idea of what the data set has. This is a very small data set that I thought that this would be very perfect for dashboarding, because you have a lot of variety in the ways a lot of variety in the data types that you have. And there can be numerous different ways in how you can input this data into the dashboard in order to get your predictions. So I'm jumping ahead a little bit, but first I want to get a good idea of how the data set, of what the data set looks like. Something that I found is pretty suspect is that a lot of the data is on very different scalings. So what I wanted to do is I wanted to play with those scalings a little bit, hopefully reduce a little bit of that error, the deviation in the predictions when we create it. But you see, the strange part for me, so what kind of led me to believe this might be in different currencies than American dollars is that typically houses in the States, if very reasonably, cost in the six-figure range, but Python shifts this up one. So the cheapest house here is about 1.7 million, which is again, it's not unreasonable or unrealistic for a house to be that much, depending on the area you're in, but it is quite a bit, especially for a minimum. So just something to keep in mind. I decided to carry forward with this because, again, like it could be in a different currency, but moving a little, and also like the area with certain areas, like it's not completely out of reason for it to be that high, but just something to keep in mind. So I wanted to play with some scaling. I decided to scale down the price and scale down the area. So the rest of the so I don't lose that So basically, I was playing like kind of a balancing act, so I don't lose that interpretability, as well as allowing the bedrooms, bathrooms, stories, and parking to kind of have more of an effect on the overall output. The next thing I want to do is separate the categorical calls and the numerical calls. So the main reason why I want to do this is so I'm able to properly encode the categorical columns using a one-hot encoding method. And this is pretty necessary, because if you ever do a machine learning model or train machine learning, a lot of ML models don't handle categorical features very well unless they already have a built-in encoding method. But this is probably one of the most important steps for our library is once establishing the save models. The save models function. So this will actually allow our dashboard to incorporate the models that we create here into the dash itself. So we first start off with the one hot encoder here. Now you might be asking yourself, why do I want to save the one hot encoder? And that's primarily because you want the encoder within your data set to consistently properly encode based on the pattern of the training set. And what I mean by that is, say you have your testing set, right? And your testing set's going to have less inputs or less lines than your training set. And when you have your training set, and when the one hot encoder is trained on your overall data set, and you try to use that the same method and transform the one hot encoder on your testing data set, you'll end up with an error, because most likely the testing set will not have all the categories of the overall set. And so you'll end up getting an error in your machine learning model when you try to predict using your testing set, where your machine learning model is you're getting less inputs than the machine learning model is getting less inputs than expected. And that's going to, a very big pain in a lot of machine learning pipelines if you're unaware of that error. So it's very important that you save the one hot encoding method you're using on the overall data set, so that we can incorporate it into our pipeline within the dashboard. Just a tip from experience. And then once you do that, you get the feature. You turn your one hot encoding data set into a data frame, and you join it together with the numerical data at the very end. And this creates our overall pre-processed engineered data set that's going to be ready for training. Now, again, as the previous speaker said, it's very important to ensure that you properly tune your model. But I just kind of wanted to make this to show you where the machine learning model is coming from. This is less about the machine learning pipeline and more about the dashboarding. So I wanted to just keep the machine learning brief and not dive too deep into the weeds with that. So I split the model into the training and test, or the model and validation sets. And then the model sets into the training and testing sets. Now, this is important because you'll essentially want to ensure that you're not overfitting when your model is done training. So once you're done evaluating your testing model, it's important to kind of test it on some external data just for that extra safety and reliability. So this is the first random forest regressor. So it's taking the training sets, taking the testing sets, and then taking the mean squared error and mean absolute error. It's not bad, but most of the time it's when you take this type of error, it's usually relative to the other models that you're using. Going here, you can see very high mean square error first, and then and you can see it kind of mellows out through the rest of them, but it definitely has an outlier. And then this is the validation set. And then I wanted to just throw in another model for comparison. So you see like the XG boost regressor. It surprisingly doesn't do as well. It probably needs to be tuned a little bit. It doesn't do as well as the random forest regressor with this one. So what we do is we train the random forest model on the overall data, or the random forest regressor on all of the data. And then when we have that trained model, we don't evaluate it this time because we're using this model that we just fit with the algorithm that we've chosen for the dashboard. So we save that to the dashboard. So now we have our encoder and our model, and we're ready to go and we're ready to dive into the dashboarding itself. So let me bring up the dashboard as a whole. Now, Streamlit is super, super cool. All you have to do to run the dashboard or to activate Streamlit is you just say Streamlit run, and then you type in the name of your application, and Streamlit will automatically run it for you. It's super, super convenient. So the first thing I wanted to start on was this introduction page. I wanted to introduce you to some of the variety that that Streamlit is capable of. So especially with the text. So going to the main application. So you see here, I decided to kind of compartmentalize this a little bit and start off with.
Oh, Alexander, I'm gonna repeat my earlier request. If you can increase the font size, that's probably gonna be so much better. Thank you.
I love Adam because it's super easy to increase the font size on it. Yep, absolutely. Thank you for reminding me again. So the first thing I wanted to start with was just a simple text-based page. So you want to start out with importing Streamlit and whatever other libraries you need. I did NumPy here, and I'll go over the utils function really quick. The utils function is basically all of the backend functions that are pre-processing the data, and but I'll go into it when we get into more of the performance, because that's when it'll become performance optimization, because that's when it'll become more necessary. So you start off with just a simple st.title or st.write. This will put text on your Streamlit page. You can kind of think of st.title as the equivalent of a header. I think it's a little bit thicker than the header because there's also st.header. But there are various ways to write out bold and large text on your dashboard. And one thing that I wanted to show you too is that Streamlit can also display images. Now, Streamlit doesn't, to my knowledge, it doesn't have an automatic display where you give it an image path. It reads the image and then it outputs it directly onto your dashboard. So what you have to do is you have to get some type of image reading library. For this example, I did OpenCV, and I did CV2 image read, CV2 image read, and that loads in the image into your dashboard, and then the ST image logo will actually output that image directly on your directly onto your screen. And then what's really cool, one thing I wanted to show you is, if you're familiar with Jupyter Notebook, you probably use a lot of Markdown. And Streamlit is actually capable of having Markdown too. If you don't know what Markdown is, it's a very flexible and robust text-based language where you're able to add and format text in a particular way in order to make your Jupyter notebooks nicer. And Streamlit's able to incorporate that to make prettier text. So in this particular example, I decided to show you a simple bulleted list using Streamlit, and then you execute the basic function in the main py. Now this is the starter page. So this is essentially the page that I want everybody to like go to whenever I start Streamlit. Now, one thing that is new with Streamlit. So Streamlit is a fairly new library. I think it's it was like a new thing about 4, maybe 3 years ago. So they've been adding on to it like crazy. And one of the new, rather new functionalities that I became aware of is when you run your main application in the overall folder, you can have this pages folder right here. and Streamlit will automatically incorporate these different Python scripts as pages within your application. So without any code at all, just setting it up in your directory, you can have a multi-page application within Streamlit just like that. So so really cool, but the directory needs to be called pages. But it's a cool trick that that they just that, to my knowledge, is rather new. So yeah, pretty cool stuff. I would like. Oops, sorry. Were you gonna say something? Yeah. So I would like to move on to the modeling page now. So this is where our model is essentially going. Now you see the number 300. You see the scatter plot and the green number here, approximate of what the predicted housing price is. Now this is the really cool thing about Streamlit. It will update based on the input. So these are what are called widgets in the flesh. So basically, by interacting with these, Streamlit will update, and you can see the number changing below. And I actually programmed this to, change the overall distribution. So you can see that red part there is the comparison of the housing price to the rest of the distribution. So you can say is the area preferred home, hot water, and you can see the price changing as you change like various attributes. This is really cool to mess around with. Now, as I said, with a lot of other libraries, doing that is a lot harder than it's supposed to be. Now with Streamlit, the really cool thing about it is these widgets essentially act like variables, or act like a simple input command in Python. So those input commands that you're used to using in a lot of your earlier applications that you created, that's what the widgets are acting like. And this is what makes Streamlit so easy to use, because not only is the formatting easy, but ensuring that these input commands are executed and laying them out is super simple. You just see like air conditioning here is st select box. So this is the select box widget that I use. And essentially that creates a true or false value, or that creates a list of options right here. That'll just scroll down and you can say yes or no. And then you have the radio option, which is a bulleted list right here. And you can play with these buttons and click around and select your option that way. And then you have the checkbox, which is essentially which returns a true or false value. I have a conversion right here. They're more efficiently used in other contexts, but I just wanted to demonstrate how some of the widgets can be utilized here. With the checkbox right here, it's false, it's true, and right here you can see a select slider and a regular slider. So these are sliders in Streamlit. It shows you a range and you pick whichever value is on the range. The difference between a select slider and a regular slider is that a select slider essentially gives you feed the widget an option or a list of options, possible options, and it will display the possible options on the slider and you move it across. So it's very useful for it's very useful, particularly for categorical values that you want to put on a slider. And the regular slider, you feed it a range of values. You feed it a minimum and a maximum, and it'll plot those values along a particular increment, and you'll be able to slide. I'm trying to go back to the dashboard. You'll be able to slide them around between the minimum and maximum. And then another widget that I played around with was the number input. So it essentially allows you to just press plus, minus, or type in another number that you wish to look at. The rest of them are very straightforward. The only other one that I did was a text input, which is very useful for a lot of natural language processing models, but I just wanted to demonstrate it here. Basically, here you have the text, which you put in freehand text, you press enter, and then that string is the input. The string that you input is the input to your dashboard, and it does whatever with it. Now, you're probably wondering, what's this? What are these with column statements here? Streamlit is, you can kind of see in if you compare the dashboards here, Streamlit has a very structured default mode. So you see this is your header, this is the image, and it kind of executes it in a stack. And what they came out with, it's not recent, but it is, it wasn't there initially, are columns. So essentially here, we split our dashboard into 3 separate columns that Streamlit is going to separate our widgets in within this body. And you can see, and basically this is super easy to use. All you have to do is just instantiate your columns above, demonstrate that there are going to be 3, demonstrate there's going to be 3 columns and what each of those columns are called. And then you say with the name of your column, execute or place whatever you want in that column there. And what's really cool about this syntax is that it's super easy to leave once you're done with those columns. Like the input, this isn't going to be, the input numbers aren't going to be a part of any column. They take they aggregate all of the inputs that we've shown above, as well as the input cats. So these columns, so these inputs are aggregated right here. But anyway, what's really cool about this is that you can very easily break out of the column format and still go for like the centered format down here. Now, what I did here with this format prediction is I wanted to show you some of the other capabilities with Streamlit. So you're noticing that Streamlit doesn't come centered. It's always off to the left. Well, if you want to play with Streamlit a little bit, you can use HTML code right here to align certain values. So what I did here is for the money, I colored it green for money. I colored the pricing green for money. I used CSS with this particular CSS within like an HTML command or HTML code. And I was able to execute an HTML component using Streamlit. So that's how I was able to get this custom text here. And if you need to, what's really cool is if you need to have like more control over your Streamlit application, you can use HTML to do that. Another thing that I decided to do here, this is the code. I don't want to dive too deeply into this. But essentially, stpyplot is what Streamlit will use to essentially plot the matplotlib plot that you have just created. So I created the histogram right here. I got the bins, the patches, and I get the selected bin that our predicted output is going to be in, and then I color that output in accordance to whichever bin. I color the bin in accordance with whichever output is there, and you can see the functions executed below. You see it reads in the data. It gets the we introduce what the page is called. We get the various inputs from our widgets, and you see it's separated into numbers and categorical. And again, like this is important because we want to encode our categorical variables. Then you get the prediction, and then you format the prediction, and that's how we get the error, or that's how we get the plot below. Now, you're probably wondering what this try and accept and ST error is. I'll demonstrate that in the analysis page. Going to the next one, this is, you can kind of see different, you can see like different plots here. This is a scatter plot that I did as well. And Streamlit also has the ability to display tables. So if you want to display like the head of your data set in your dashboard, you're able to do that as well. And in this sample, I made it so you can add as many bar charts as you would like here. So you can get an idea of various distributions. And then this is where that error handling is. So ST error is essentially Streamlit's method of error handling. And what you can do is you can essentially throw the user an error in order to get a proper input from them. So this only comes with a pair because it's a stacked bar chart. So if I take one of these out, it'll throw an error to me because it's expecting 2 columns. So if I added the other one in, you can see the stacked bar chart is still prevalent on here. Now, for the numerical columns, Streamlit, this is not a matplotlib plot. Well, technically it's a Seaborn plot where this comes from. It's able to be handled by Streamlit as well. Basically here you see the scatter plot between price and area, and it's colored by a various number of categorical columns that are present within the Streamlit dashboard. So you see the bathrooms, stories, and so on and so forth. Now, going into the code here for the analysis page, you can kind of you start with the separations. So this is very similar to what we did before. We decide to iterate through the columns, except this time I want to separate the nominal columns from the numerical columns. So basically, this piece of code, if the sample value is less than 10, now this isn't the best way to separate nominal values. There will be some nominal values that are that are greater than 10, or some more continuous values that are less than 10. But in this particular case, the smallest continuous value, I believe, was like 1,000. So this is a pretty safe way to extract all the nominal values. So once we get those, we create our bar chart. We create like our basic bar chart where we use what's called a multi-input in order to actually, I'll go down here. It's because I want to demonstrate the widgets rather than matplotlib. You see down here going through the tabs. This is a multi-select. Now, multi-selects are really cool because they essentially return a list that the user has selected multiple values from. And that is essentially how we're able to choose how many bar charts we want to plot, how many the pairs that we want to select. And from that, we're able to actually display those onto our dashboard via the user input. So multi-selects are very, very powerful. Now we take those multi-selects we take the value from the multi-selects right here, and we create our figure size, and we enumerate through our list that the multi-selects gave us. And we're able to plot each subplot next to each other on the dashboard. And then, and essentially, like, we take the selected values, we group them, we count them, and then we plot them on the bar chart next to each other. And then we display this figure using st.pyplot. Similarly, we take the selected pair from our other multi-select, and then we unpack that selected pair. We group by the selected pair. So this is a double group by. So this will create a hierarchical grouping within our data set. And then the unstack will essentially take one of our indices and place it as the columns. And then we have another one of our indices and we place that as the rows. So once we do that, we're able to have a data set that we're able to plot. And this particular data set, I decided to plot as a stacked bar chart, and then use st.pyplot to get the figure on the dashboard. Now for the error handling, similarly as I introduced before, it'll throw an error here if the user only has one column because the code isn't able to execute on one column. It's anticipating two, since it's the stacked bar chart. Now for here in the except statement, I threw an error that says, please enter another column. So when the user only enters 0 columns, then it will say this. However, if it's an unknown error, it's again like use try and accept statements for error handling very responsibly. One thing that I like to do is if there's like a condition that I can place upon it, then I place a condition in the accept statement just to check to make sure that the error is exactly what I'm hoping for. If the error isn't, then I have this statement called unknown error, but hopefully it won't come to that, especially because since I limited, the multi-select is able to be limited to a particular max selection, and I chose 2 here. So that's essentially like how it's able to, or how I'm able to prevent it from going further. I'm pretty sure there's a min selection, but I just wanted to demonstrate. How the error handling can be done. The other thing that you'll see that's different here compared to the other page are tabs. Now, tabs can be very, very helpful in further organizing your dashboard. So that's essentially what this does right here. You can see switching between them. It hides information and makes it more palatable, or more visually pleasing. And what's really cool is tabs work very similarly to the columns. Again, Streamlit syntax is very simple. All you have to do is instantiate your tabs up here. Say name the various tabs that you're going to use, and then unpack them into the number of variables that you've named. And then here you can see the code separated into the different tabs using the various functions. So like the bar charts I put in one tab up here, the scatter plot I put into another tab down here. And I believe that I kind of glossed over the scatter plot. So basically, the scatter plot only accepts one. We use the select box for the column in the scatter plots, and it selects one. It takes one of those columns and then puts them in the scatter plot as the hue, and the area and price will stay the same. So it takes the selected column, makes it the hue, and that's how we're able to color the scatter plot. Based on various inputs. Now, we've gone through most of the dashboard. We've gone through the modeling page, which essentially takes the group of inputs here and creates an output underneath, and it will map the output below. And then we took the analysis page here, which can take multiple variables and essentially demonstrate to the user convey various levels of information to the user. And we have our tab function here, and we have our scatter plot that's shown here. We even have our data sample here. Now, and of course, we have our introductory page, which gives the user like an idea of what they're in for. And so basically, the only thing that I have left to explain in the dashboard are the utility functions. So the util functions are essentially backend functions that don't really have a lot of front end ability, but they assist. They're very, very important to handling a lot of the data. Now, we can start by looking into just a simple read CSV function. So you're probably wondering why I decided to put this read CSV in a function rather than actually, use the function that Pandas provides me. Well, the key is this st.cache data over here. Now, for performance optimization, what's really cool about Streamlit is it comes with these different cache commands, or these cache decorators on top of your that you can use with your Python functions in order to store the read-in data or whatever read-in resources you have for your dashboard. so that it increases performance. Remember when I said that Streamlit, whenever you make an input command, it'll rerun your script in its entirety. Now, that can be now the data set's pretty small for this example, but with Streamlit, every single time you use an input, it'll repeat that command, and it tends to get rather lengthy if you are reading in a very, very large data set, like especially with when you're dealing with big data. The advantage of this cache data is that it will keep the data set, or keep that data read into your dashboard, so that every single time you make a command, it'll already have that data read in, so the user will be able to input more commands without having to wait for that buffer, of the data being read in over and over and over again. So cache resource is a very, very similar concept, except this is done with models. So you notice that this decorator is above the load models function. And oh yeah, by the way, let me back up for a second. If you don't know, a decorator is essentially like external. They act as external behaviors that a particular function, that you can give a particular function in order to have it behave a certain way. Now, these cache resources are the caching external function is the behavior that I wanted to exhibit, and that basically gives Streamlit the ability to save whatever is in the return values of these functions in the dashboard. So just a little Python lesson. Decorators are very, in my opinion, very underrated techniques. They can save you tons of lines of code and make your code extremely readable. But anyway, all you have to know is like these. The main function of these decorators is primarily for optimization. And essentially, they take whatever, they're a signal to Streamlit that we want to keep whatever is read in, so we don't have to continue rereading it in again. Now, as I said before, we load in the encoder model. We don't want to remember, we don't want to create a new one, because if we create a new encoder and fit transform on the input, we're going to have 6 values that we're going to have not 6 values. We're going to have many values that our model is expecting that it will not get. And because of that, we want to load in our predefined one-hot encoder model. And when we load that in, we just use the transform function on our categorical inputs in order to get our actual encoding. And then once we encode it, we send it to an array. And then I made this function called finalize inputs, which will take the numerical inputs and the categorical inputs and put them together, or more like the encoded categorical inputs, put them together, and then make sure to reshape it. Oh yeah, by the way, make sure to reshape your arrays if you're dealing with, especially when you're dealing with like a dashboard, because what ends up happening is your NumPy arrays will be in the shape that will essentially just be like a 1, whatever length your NumPy array is, and it's expecting features rather than length. So what you want to do is this -1 len cat inputs here will essentially make it a width rather than a height. And by making it a width, like your models can actually act on the singular input. It's a very, very common error. Believe me, if you go on Stack Overflow, if I had a nickel for every time somebody asked this, I'd be a very rich person. So make sure to reshape the arrays once your inputs are done. And then the final thing we do is load in our model and then make the predictions. And that's pretty much the entire dashboard here. So putting it all together, you can see we have a very comprehensive dash where we're able to not only analyze the data, but use our random forest regressor to take our data and predict future values with it. Yeah, and that's pretty much the end of the presentation. I hope you all enjoyed it.
Yeah. Hey, Alexander. Yeah, I enjoy it. And I mean, I hate coding front end and all of that. So this is gonna save my life. Thank you pretty much too. Anyway, I will bring up Yannick, and he will take care of the. Hey, Yannick. All right. Thank you, Alexander. Thank you, Yannick.
Excellent. Well, thank you again, Alexander. And everyone, tout le monde, je le dis en français aussi, vous pouvez taper vos questions sur YouTube ou sur Slack en français ou en anglais, puis moi, je vais les traduire. Ça va me faire plaisir. So everyone, you can type your questions on Slack or on YouTube, and I will relay them to Alexander. We already have a question. Well, there was a question, and you answered it as you were explaining everything. So this one is covered. But Jean-Philippe Brochu is wondering if you can export the dashboard so you could, let's say, email it to someone without having to host it where they would be able to access it.
That is a really, really good question. I remember I remember somebody asked that on the website. I will have to get back to you on it. The good thing is, though, the good thing is with Streamlit is that it's very easy to run as like a complete file. So if you send someone, actually it's deployable with Docker very easily. So if you're able to, if the person receiving it has a computer set up with it or some type of way for handling Docker files, what you can do is you can deploy your Streamlit dashboard on Docker, and then send them the file with Docker, and then all they have to do is like Docker compose up or Docker build, and they're able to run your dashboard locally. So in terms of like whether you're able to save it as like a PDF or some type of special file, and then or save it as a PDF and then send it over, I'm unsure about that particular functionality of Streamlit, but sending Streamlit back and forth via stuff like Docker or just simply running it inside of your own browser is very easy. That is a really good question.
Excellent. How small can you get those Docker images? Typical Docker image tend to have a lot of let's say dependencies built in. So maybe not super email friendly, but what's your experience? What's the minimal size that you can get with?
Ooh, now that is another good question. Let's see. I don't really have a particular number in terms of like megabytes, if you're wondering. But most of the time when you run a Streamlit application, you're at least going to want your Streamlit library, some type of scikit-learn or some type of machine learning library that you're using, your pandas function or your pandas library, and then maybe something like NumPy. But sometimes you can like restrict it a little bit, but most of the time like NumPy. So at least those and maybe like pickling files in order to load in your models. But yeah, other than though, like typically you can restrict it to those dependencies, but it can get but depending on how complex you want you make your library, like the requirement for Streamlit can get like greater and greater. Like I remember I did it recently and it was way too big to email as you brought up.
Very good. So I don't see any other questions. I have a question. So you showed us Streamlit running standalone with its own built-in server.
Yeah.
Is there a way that you would be able to integrate it inside another URL from a Whiskey app, or is this something that you would let your reverse proxy remap the URL and you have the port specific to Streamlit?
Oh, absolutely. I'm very happy you asked that. Man, it's going to sound like I'm a salesman for Streamlit, but it's open source. So Streamlit actually recently released a cloud edition that allows you to deploy your models your models for free onto their community cloud. And that's essentially how they build up their community and allow different people to interact with other people's different models. So that's the free solution. And to my knowledge, it is compatible with different applications like Heroku and other methods of deployment in order to make it from a local to deployment to like more extensible. But I'm very happy you asked that, because I was hoping to bring in the community cloud into this conversation somehow.
Very good. Excellent. So let me double check. I don't see any other questions. There's a lot of very positive comments that are not questions. I invite you to take a look at YouTube once you have a moment. But that will conclude our presentation today. So thank you again, Alexander.
Right. Thank you, Alexander. See you later. Yeah.
Yes, it was my pleasure. It was so much fun to do this. I love working with Streamlit. It's one of my favorite things.
We saw that. Yeah. Anyway. Ok. Je vais te garder avec moi, Yannick, parce que c'est la fin déjà. Quand même, on a fait plus long que d'habitude, mais je vois que c'est super le fun que je vois pas le temps passer. Fait que c'est ça, on va finir ça. Je veux juste vous rappeler que le 24 avril, ça va être, je pense que j'ai dit en personne, mais je pense que ça va être plus, notre prochain événement, ça va être plus en mode hybride. Fait qu'on va essayer de faire un setup pour que les gens puissent aller online si vous ne voulez pas vous déplacer. Si vous voulez nous rejoindre à Flair System, vous êtes les bienvenus. Puis, c'est ça, envoyez-nous votre proposition de présentation, puis on attend ça. Est-ce que tu peux répéter ça, Yannick? Oui.
Okay, I say it again in English. So Montreal-Python 99.2, volcanic neologism. Neologism volcanic. Will be on April 24th at Flair Systems in Montreal, near the La Chienne Canal. And it's going to be a hybrid session. So if you can't make it in person, we will still stream it or have a way for you to watch those videos if it's not live streamed. And please send us your talk proposals, because we want to see you in person. Give us some talks or online if you cannot make it in person for presenting.
Yep. OK, cool. Je pense que c'est tout. On s'en va à notre after hour.
Ben oui, mais là, il faut dire aux gens comment rejoindre ce after hour. Donc, j'ai mis l'URL ici. Si ça ne vous tente pas de la taper, elle devrait être dans les commentaires, pas dans les commentaires, dans la description du vidéo sur YouTube. Et c'est ça, on va se voir là-dessus dans un moment.
OK, c'est bon. Merci beaucoup tout le monde et à la prochaine. Bye bye.